Question number 17. A 12-volt battery has an internal resistance of 2 ohm. So let's draw a battery. So this is a battery here, and it has an internal resistance of 2 ohm. 2 ohm. And the EMF of the battery is 12 volt. I guess this is a battery with internal resistance. Okay. And a load of variable resistance is connected across the battery. So there is an external load. It's connected across the battery, and the external load has some resistance R. It's a variable resistor, so it looks like this. This is a variable resistor, and this is the internal resistor. Small r. So this is small r. This is capital R. This is 2 ohm. This is unknown. A load of variable resistance is connected across the battery, and it just has to have resistance equal to that of the internal resistor. So it looks like the small r internal resistance is equal to capital R, which is external resistance. Which statement is correct for this circuit? Then do you remember from the data booklet we have this equation for the internal resistance? I'll show you where it is. This one. Epsilon EMF equals to current bracket capital R plus small r. Which statement is correct for this circuit? The current in the battery is 6 ampere. I don't think so. Let's see. We know that the resistance is V over I, so make I the subject, which is equals to V over R. The total voltage provided by the battery is 12 EMF, and the total resistance of the circuit is R plus R. We have to add them together because small r and capital R both are in series. In series, the total resistance gets added up together. So 2 plus 2 is going to be 12 divided by 4, which is definitely not equal to 6. So A is wrong. The potential difference across the load is 12 volt. Well, as you can see, in this circuit, there are 2 resistors in series. So the total voltage or the total EMF must be divided among these 2. If both of them have same resistance, then each one of them should share a voltage of 6 volt, half of it. So it must have 6 volt, and this one should also have 6 volt. Both of them should have equal voltage across them because they have same resistance. 12 volt is divided into 2 parts, 6 and 6, so that 6 plus 6 gives you 12 volt. So it's wrong. The power dissipated in the battery is 18 volt. Power dissipated in the battery is 18 volt. So this is a whole battery, and so this battery is dissipating or losing some power. Now the power lost by the battery is because of the presence of internal resistance. So we already know that there are 3 different equations for the power. Power equals to IV, I squared R, which is also equals to V squared over R. Yeah, I will suggest use the third equation because we don't have any information about current here. We could find the current first by using this method, but there's no point of doing more work. It's an MCQ, so we have to be very straightforward and smart about the question. So how much is the voltage across the internal resistor? Well, we found out it to be 6 volt. Why is it 6? Because the internal resistor and the external resistor, they both have the same resistance. Same resistor means they will equally share the voltage of the EMF. So the EMF is 12, 12 divided by 2 is 6 and 6. If there were 3 equal resistance, then it will be 12 divided by 3. So 6 and the resistance is 2. So 6 squared is 36 divided by 2, which is 18 watts. So 18 watt of power is lost across the battery. So it has to be 18. Just for extra practice, what do you think is the power dissipated across the external resistor? Well, it's the same. V squared over R. How much is the voltage shared across the external resistor? 6 squared. And how much is its resistance? Its resistance is the same as the internal resistor, which is 2. So the answer is still 18 watt. So this guy is also releasing 18 watt of power, and the battery is also dissipating 18 watt of power. Okay? Question number 18. A wire carrying a current I is at right angle to a uniform magnetic field of strength B. A magnetic force F. So a wire carrying a current I is at right angle to a uniform magnetic field of strength B. A magnetic force F is exerted on the wire. Which force acts when the same wire is placed at the right angle to the uniform magnetic field? Okay, so we have to go back at the data booklet and see we have really used this equation. So the magnetic force generated is equals to BIL sine theta. So B is the magnetic field strength, I is the current passing through the magnetic wire, through the conducting wire, and L is the length of the wire inside the magnetic field, and sine theta. Theta is the angle between the normal component of the magnetic field and the wire. This theta is the angle between the current carrying wire and the magnetic field. So this is the magnetic field. So this angle can be 90 this time. This angle is theta. Okay. L is the length of the wire inside the magnetic field. Let's use that equation here. So we know that the equation of interest is F equals to BIL sine theta. So this is the equation that we will be using. Okay. And so what is our... So you can see the angle is right angle. So right angle means this will be 1. Why? Because sine of 90 degree is 1. So we can ignore this part. So here we have F equals to BIL. Yeah. So sine theta is equivalent to 1 because the angle is 90 degree. So our new force is equal to new magnetic field strength, which you can see is twice the original magnetic field strength. How much is the current? Current has reduced by a quarter, and the length of the wire, well, it's the same length of the wire inside the magnetic field. So you can just do some mathematics here. It's going to be 1 over 2 BIL. So if you also realize, what is this BIL? This BIL is the original force. So it means that our new force, new magnetic force acting on the wire, is equals to half the original force. It's going to be half the original force as B bar. An object at the end of a wooden rod rotates in a vertical circle at a constant angular velocity. What is correct about the tension in the rod? So imagine this is the center of the rotation, and this is the string, and there is some mass attached to it. Let me draw a little bit smaller. And this thing rotates in a circular fashion. So vertical circle. So vertical circle in vertical circle we have to take into account of the weight, the gravity. So weight equals to mg. This is probably rotating like this. So you can have this position, or this position, or you can also be at the top position. Okay. An object at the end of a wooden rod rotates in a vertical circle. So vertical circle. So we have to take into account of the gravity. Weight equals to mg, which acts downward at a constant angular velocity. What is correct about the tension in the rod? Well, first of all, you need to realize that it's a circular motion problem. In a circular motion, we must always have a resultant net centripetal force. So this centripetal force must be a net force acting toward the center of the circle. So it must be net, and it must be acting toward the center of the circle. So we have two extreme cases. One extreme case is when the ball is right on the top, and when the ball is right on the bottom. So when the ball is right on the top, you can see still there is a circular motion occurring. So for a body to move in a circular motion, there must be a centripetal force, a net centripetal force acting toward the center of the circle. So call it FC, and it is a net force. Now, who is responsible to provide this net force? Well, it is the job of the tension in the wooden rod. Well, the tension doesn't need to do a lot of work here because the weight is in the favorable direction of the tension. So you can see the weight is acting downward, and the net centripetal force also needs to be downward toward the center of the circle. So the tension doesn't need to provide a lot of force. So tension just needs to provide any extra amount of force that is required in the downward direction to make sure that it becomes equivalent to the net centripetal force. So the tension will be a minimum when the ball is at the top position. But when the ball is at the bottommost position, as you can see here, we still need centripetal force toward the center of the circle, and it has to be the net force. Well, this net force is still provided by the tension, but this time the weight is in the opposite direction of the tension. It is not in a favorable direction, so hence the tension need to be greater so that it can not only overcome this weight, but also provide extra centripetal force that is required for the body to move in a circular motion. So the tension will be maximum at the bottom because it has to overcome the weight first and then provide additional centripetal force as a net resultant force for the body to move in a circular motion. So it will be greatest when the object is at the bottom of the circle. Okay? Question number 20. Which of the following lists the particles emitted during radioactive decay? So radioactive decay is the breakdown of heavy. So radioactive decay is the breakdown of heavy, unstable, and lower binding energy nuclei into smaller but more stable and higher binding energy nuclei. Emitted during radioactive decay, so the radioactive particles that are produced during the decay process can be alpha, beta, or gamma, in order of increasing ionizing power. So you need to know what ionizing power is. Ionizing power is the ability of the particle to knock out the outermost valence electron of an atom. So for example, an atom has a nucleus, right? And the nucleus contains protons and neutrons, and protons are positively charged. So overall, there's a net positive charge on the nucleus. So outside the nucleus, you have these electrons that revolve in the electron orbital shell. So you have these electrons here, and these electrons are like negatively charged, right? So, for example, if you have like an alpha particle, a heavy alpha particle which has like 4 and 2 here, and when this alpha particles collide with the outermost shell of an atom, what it does is it knocks out the outermost valence electron of an atom. When it does that, there is electrical instability developed. What it means is, now before the atom was electrically neutral, meaning it has 0 charge because it had equal number of negative electrons and protons, so there was an electrical stability and balance. So there were equal number of electrons in the shells and equal number of protons inside the nucleus. But now you have more protons than electrons because some of the valence electrons, outermost electrons, have been knocked out by the radioactive particles. So the ability of the atom or the particle to knock out the valence electron, the outermost electron of an atom, and hence making it to develop a positive charge, is the ionizing ability. And this ionizing ability is directly proportional to how much mass or heavy or momentum of the particle. So bigger the momentum of the particle or bigger the mass, the heavier it is, it means it has a higher ionizing power. It has higher ability to knock out the outermost valence electrons of the atom, hence causing the overall atom to develop a positive charge because it will have less number of electrons than protons left behind. So in order of increasing ionizing power, alpha is the heaviest of all because it has like 4 nucleons, 2 protons and 2 neutrons together. And then you have this beta. So beta has like it has like around no mass, but it has like 1 charge. It can either be a positive beta or it can be a negative beta. So beta has an equivalent mass of an electron, so it's not very heavy. Gamma has no mass at all because gamma is an electromagnetic wave. So this will be a decreasing order of ionizing power, alpha being the most ionizing and gamma being the least ionizing. In order of increasing, so increasing will be alpha will have the greatest ionizing power and beta, alpha and the gamma will have the lowest ionizing power because gamma is just an electromagnetic wave. Gamma, however, has the highest penetration power, so the ability for it to penetrate through an object is highest for gamma. So in terms of increasing penetration power, it will be alpha being least penetrative because it can be blocked by a few centimeters of paper, or it can be just blocked by one single paper, or 10 centimeters in air. Beta, it will need like at least 2 centimeters of thick paper to block beta particles, and gamma, in order to block gamma, you will need like a thick piece of lead, a bulk thick piece of lead to block gamma. So in terms of increasing order of penetration, it will be alpha, beta, and gamma. But in terms of ionizing power, it will be gamma, beta, and alpha. Okay. Question number 21. When an alpha particle collides with a nucleus of nitrogen, so we have a nitrogen here that has like 40 nucleons, 7 protons, plus it collides with alpha. Alpha has 4 and 2. Okay, let's see what happens. A nucleus X can be produced together with a proton. Okay, now we have to conserve all type of nucleons charges together. So total number of protons and neutrons have to be conserved on both sides of the equation. So let's see. For this one, how many protons and neutrons do we have for these two? Okay. Now, let's write. How about that? So protons. So there's a proton here and neutrons. So how many protons does the nitrogen have? It has 7 and 2. How many neutrons does it have? So we have to take the difference between the two, because 14 means sum of neutrons and protons. So it's a nucleon number, which is a sum of protons and neutrons. So 14 minus 7 will give us 7. 4 minus 2 will give us 2. Okay. So this is the case. So let's see if we add them together, how many protons do we have in total? So in total, we have 7 plus 2, 9 protons and 9 neutrons. Okay, so it looks like we have to give away 1 proton. As a result, there will be only 8 protons left behind. And how many neutrons do we have? We have 9 neutrons. So on the nucleon number, we have to add up the neutron with the number of protons left behind. So 9 plus 8 will be 17. So it will be 17 and 8. The mass defect of deuterium, this is an isotope of hydrogen, is this much. What is the binding energy of deuterium? So the binding energy formula is given by this equation. So energy equals to mc squared. I'm sure everyone has seen this equation before. So the binding energy released is as a result of the mass defect present times the square root of the speed of light. Now this equation will give you everything in SI units. We also need to make sure that all the terms here is in SI unit. So speed of light is in meter per second, mass is in kg, and that will give us energy in joule. Okay. Alright, so in this question, all of our options are in terms of electron volt, and electron volt is just a different unit of energy. So the SI unit for energy is joule. The SI unit for energy is joule, and a different unit for energy is also electron volt. So electron volt and joule, both of them are a form of energy. So they are actually interchangeable. So if you want to convert electron volts into joule, you just need to multiply by 1.6 times 10 to the power negative 19. And if you want to convert from joule to electron volt in a different unit, then you just need to divide by 1.6 times 10 to the power negative 19. So this 1.6 10 to the power negative 19 is elementary charge. 1.6 10 to the power negative 19 here. It's elementary charge. It's given in data booklet. This is the conversion. Alright, this time, since this equation gives everything in SI units, so C is speed of light meter per second, M is the mass defect in kg, that will give us the mass defect in joules. So we need to convert the mass defect in joule into electron volt. To do that, so to convert joules into electron volt, we need to divide by the elementary charge, which is like E. So we will input the numbers in the end. Okay. So the mass defect is 4. 4 times 10 to the power negative 30 times speed of light, which is 3 times 10 to the power of 8. This is also given in data booklet. And then take the square. Let me show you where it is. There it is. Speed of light in vacuum, 3 times 10 to the power of 8. Square, and then dividing by elementary charge, which is 1.6 times 10 to the power negative 19. Alright, now we have to use some mathematics there. It's going to be 4 divided by 16. 1.6 times 3 square is 9, and then multiply by 10 to the power negative 30. 8 times 2 is 16, so plus 16, use indices. Minus 19 goes up, becomes plus 19. Okay, so 9 times 4 is like 36. So we have 36 divided by 1.6. So 1.6 can be actually written as 16, and you can put like one more 0 here. So it's easy to calculate, right? Times 10 to the power, and this is going to be negative 3 plus negative 15, negative 15. Yeah, negative 15 plus. This is going to be 5. 360 divided by 16 is around 2.25 times. No, it's going to be. Calculators are not allowed, just do it by hand. 22.5 times 10 to the power 5. Standard form, scientific form will be 25 times 10 to the power 6. So which answer is closest to this one? It's going to be approximately 2 times 10 to the power 6. You can see this is the answer. It's around electron. Okay? Alright, good. Yeah. So number 23. What are the principal energy changes in photovoltaic cells? So photovoltaic cell, and solar heating panel. Okay, so photovoltaic means photo means light. Voltaic comes from the electricity, so it has to be light or solar energy to electric. So solar to electric is photovoltaic cell. So ignore B and D. And solar heating. So think solar is again light, right? So solar. So ignore these two. So solar to heat. Heat means thermal energy. So the energy conversion is from solar to thermal energy. So it's going to be 8. Okay. The solar constant is the intensity of the sun radiation at the surface of the Earth. Solar constant is the intensity of the sun radiation at the surface of the Earth? No, because if you see, if this is the sun is radiating solar energy, and this is the Earth, the entire surface of the Earth doesn't receive the solar intensity from the sun. It is only the front face, the front side of the Earth that will receive the energy. See here? That is why, so for example, this side will be daylight and the back side will be nighttime because there's no light reaching the other side of the Earth. Only the front side is receiving the light, right? The solar constant is the intensity of the sun's radiation at the surface of the Earth? No. The surface of the sun? Absolutely not. The 10 kilometer, no, there is no standard. It's the mean distance from the sun of the Earth's orbit around the sun. Yeah, so it's the mean distance. The mean distance from the sun to the Earth orbit around the sun. Yeah, another reason is because the orbit of the Earth around the sun is not perfectly circular. So it's actually elliptical, so we take the average. We take the mean distance of the orbit and then we use it to find the solar constant. Okay. So number 25. X and Y are two spherical black body radiation that emits the same total power. So the total power radiated is the same. The absolute temperature of X is half of T. So it's like the power radiated by X is the same as power radiated by Y, same total power. And it's a black body radiator, so if it's a black body radiator, then the emissivity has to be equals to 1. Remember, emissivity is between 1 to 0. If it's 0, then it's perfectly white spherical body, which doesn't emit or reflect. It doesn't emit or radiate any thermal heat radiation. It's a perfectly reflector of radiation. And if the emissivity is equals to 1, then it's a perfectly black body, which is a perfect absorber and radiator of radiation or thermal heat. Okay? The absolute temperature, so, and also the absolute temperature of X is half that of Y. Absolute temperature means temperature in Kelvin. What is the radius of X? And it's a spherical body. It's a spherical body, so it's a sphere. The surface area, the outer surface area of the sphere is 4 pi r squared. So that's the formula for the curved surface area of the sphere. Okay, so we have to use the black body radiation equation from the data booklet. I can show you where it is. So if you just scroll down to topic 8, and this one. So power radiated is emissivity, the Boltzmann constant, curved surface area, the outer surface area, and T to the power of 4, the temperature in Kelvin to the power of 4. Okay? And this sigma is a Stephen Boltzmann constant, so it's different from the Boltzmann constant we learned in topic 3, the thermal heat and thermal heat capacities. So remember, so just know how to use this equation. Okay. So we will just copy that equation here first of all. So we know it's a E sigma A T to the power of 4. So this is the equation that we will be using. So these two powers are the same. So we will say, oh, emissivity sigma area of X T to the power of 4 or 4x. Emissivity sigma Stephen Boltzmann constant cross outer surface area of Y, temperature of Y, absolute temperature to the power of 4. So we sub in the power equation into here, make them equivalent. Okay. Then you can see since both of them are black body, and probably they have same emissivity equals to 1. And Stephen Boltzmann constant is also constant, so it must be the same. Okay. Now we can sub in the formula for this surface area of a sphere. So area of X is 4 pi radius of X to the power of 2. And temperature of X to the power of 4 equals to, again substitute the surface area of a sphere formula into area of Y, and R of Y to the power of 2, temperature of Y to the power of 4. You can see 4 pi and 4 pi further cancels out, and we need to make radius of X over radius of Y the subject. So radius of X squared over radius of Y squared. You can see this radius of Y squared can bring down here, temperature of Y over temperature of X to the whole power of 4. You can take this to the power of 4 common out using indices rule. Okay? And then also, you can also further write it as like this. Take the square common out, Y temperature of X to the power of 4. And to get rid of this square, take square root on both sides. This and this cancels out. So we have R of X over R of Y equals to, as you can see, we have 4. 4 times half is T of Y over T of X to the power of square root of to the power of 4. So you should also know that square root of something is something to the power of half. So half times 4 will give you 2. Okay? So there we have it. So we have radius of X, so radius of Y equals to something with square. For the denominator, we have temperature of X. So if you look at this equation, make temperature of Y the subject, it will be 2 times temperature of X. So 2 can go from there. 2 times temperature of X. So you can see this is cancelled out. So 2 squared equals to 4. So that is why A part is the answer. Okay. Alright. Now just be careful here that square root of to the power of 4 is just 2, because 4 times half is 2. Okay. A particle is oscillating with superharmonic motion HPM of amplitude x0 and maximum kinetic energy EK. What is the potential energy of the system when the particle is at the distance of this much from its maximum displacement? Okay, let's draw a diagram here. So call this the equilibrium mean position where the displacement is 0, and call these the amplitude where the displacement is like maximum. Okay, and maybe let this be the positive displacement, and the other one will be the negative. So maximum kinetic energy EK. So you know the speed of the body in superharmonic motion is maximum when it is at the equilibrium mean position. So this will be the point where the particle will have maximum kinetic energy, and that maximum kinetic energy is EK. What is the potential energy, stored elastic potential energy, of the system when the particle is at the distance of 0.2 x0 from its maximum displacement? So this is maximum displacement, and when he is this much meter away, so 0.2 x0. So in other words, he is somewhere here. Okay, so at this point, it doesn't matter if the body is moving toward right or left, the sum of kinetic and potential energy will be the same. So this body will have same kinetic and potential energy irrespective of its direction of motion. Okay, at this point, so we're only concerned with the magnitude of the displacement from either side, either from the equilibrium position or from the maximum displacement from the amplitude. It just doesn't matter. Okay. Let's see what are the formulas for the maximum kinetic energy. So if you can see here, the formula for this is the formula for the kinetic energy, and this is the formula for the total energy. Okay. So as you can see here, there is no formula for maximum kinetic energy, but we have to be a little bit clever here. Well, if you remember the graph of superharmonic motion, if this is like the negative amplitude, this is like the positive amplitude, and this is the equilibrium mean position, this is the graph of kinetic energy, and this is the graph of potential energy. So this is for EK, and this is for E potential energy. And you can see at this horizontal line is E total. Total energy of the system stays conserved, it stays the same because it is the sum of potential plus kinetic energy. Okay? Now, at this point, we have EK, which is maximum, right? Maximum kinetic energy. So you can also say that, oh, the point at the equilibrium position where the kinetic energy is maximum, that is a point where we don't have any potential energy. Since total energy is the sum of kinetic energy plus potential energy, if there's no potential energy, it means like the total kinetic energy is just due to the maximum kinetic energy. So the total energy is entirely due to the maximum kinetic energy. There's no potential energy. So EK is actually equivalent to this formula. Okay? So we can go back to our, we can say okay, that our maximum kinetic energy is actually given by this formula. So we can say E k equals to half m omega square x naught square. This is from the data book that we just derived. So that is what we have at this position. Okay, in the next step, we will see what is the kinetic energy at a certain displacement. So this equation, in this equation, everything is a constant. M omega x naught is constant except for x. X is the displacement from the mean position, equilibrium mean position. Let's copy this equation here. So we say that the general formula for the kinetic energy is half m omega square x naught square amplitude, which is constant, and this is the amplitude, this thing is constant, minus x squared. Okay, let's find out how much kinetic energy is left when the body moves from here to here. Because at this position, the kinetic energy of the body is maximum because there's no potential energy, and it is also equals to the total energy. So as the body moves from here toward the amplitude, the kinetic energy starts to drop. So a loss in kinetic energy is converted into gain in potential energy. So let's figure out what is the kinetic energy left behind at a distance. How much is the displacement from here to here? Well, if the total is x naught and this distance is 0.2, then you can see x naught minus 0.2 x naught will give us 0.8 x naught. Let's figure out how much is the kinetic energy left behind at a distance of 0.8 x naught from the equilibrium mean position. Okay, let's do the calculation here. So it will be half m omega square x naught squared minus 0.8 x naught whole square x. Okay? Okay. So behind here we have to do a little bit of mathematics. So we still have half m omega square. Omega is the angular velocity. We have this x naught square still. What is 0.8 square? So 0.8 square, let's see. So you know that 8 square is 64. So this is equal to 0.8 times 0.8. You can see we have to go backward 2 zeros. 2 zeros going backwards, so we have to divide by 100. So go 2 zeros backward. So 0.8 square will actually give you 0.64. So here we have 0.64 x naught square. So these are two like terms. So what is 1 minus 0.64? This is going to be 0.36. So this entire thing is going to be 0.36 x naught squared. Okay, let me write down the kinetic energy available at that distance. So kinetic energy available at that distance is half m omega squared, and then we have 0.36 x naught squared. Or in other words, take 0.36 x naught squared out. 0.36 just 0.36, and then times half m omega squared x naught squared. Okay, they are equal. Okay, now what is the amount of kinetic energy left behind? So what do you think? So because we know that total energy is kinetic energy plus potential energy. So in order to find potential energy, we need to subtract the total energy available minus the kinetic energy left behind at that point. So the total energy is here. This is the total energy, which is half, or in other words, just write it as EK. Okay, minus. Now realize what is this? What is this? Isn't it half m omega squared x naught squared? Half m omega squared x naught squared. Isn't this EK already? Exactly. So this entire thing is just equals to 0.36 of EK. See how small it is? Okay. So minus kinetic energy available is 0.36 of EK. So let's subtract it. So it's going to be 1 minus 0.36 is 0.64. Okay. There it is, our final answer. 0.64 times EK of potential energy is left behind. Monochromatic light. So monochromatic means light with single wavelength, right? So light with just one type of wavelength, single wavelength. is incident on a double slit. So it's no longer a single slit problem, it's a double slit. Both slits have finite width. The light then forms an interference pattern on the screen, some distance away, which graph shows the variation of intensity with distance from the center of the pattern. So this is never correct. The intensity always drops as you go away from the source. Okay. We are never seeing this kind of pattern, so it's either this or this. Actually, no. We have seen this type of pattern. Not necessarily like this, but it's pretty close. So probably if it was just like this, if this wasn't there, all these ripples, if it was just like this, then this will have been for single slit. But when it comes to double slit, then only then we have these small ripples. So all these ripples and further division is produced in a double slit problem. So this is for a double slit. So in the double slit, the single slit wave, so this is the single slit wave that I'm drawing. So as you move away from the source, the intensity drops. Imagine if there were no ripples, it would have been a single slit problem. But if there are ripples, then it means it's a double slit problem. Okay, so it's either C or D, but this time since it's a double slit, it's going to be part D. All right, light of wavelength lambda is incident on a diffraction gradient that has a slit separation of 7 lambda over 2. Okay, let's draw this diagram here. So this is the slit width, and these are the wavefront that are approaching the slit width, wavelength of lambda, and this is D, and here is our D. Okay, so here's our wavelength. So imagine this is the imaginary line, and this is the screen. This is our screen. This is the back side of the screen. Okay, this is the back side of the screen, and you know that this distance is like capital D. Normally the equation that we use is this one, S equals to lambda D over small d. Okay, this time we will use a little bit different equation here, similar but a little bit different. Now, what is the greatest number of maxima? Maxima are constructive interference. So you can see we have maxima here, and then maxima here, and then maxima here. So between two maxima we have minima. So there's a minima here, call it dark spot because minima is where the destructive interference. Let's give it a red color maybe. Minima is where destructive interference happens. Destructive, okay? And this is the maximum. This maxima is always there, and this is the central maxima. These two. So the distance between the central maxima is actually 2s, and half the width between central maxima is x. Okay. Now, in order to find the greatest number of maxima, realize that first maxima will hit here, right? Second maxima will hit here at a certain angle, and then we have third maxima, and then we have fourth, and on and on and on. As long as this angle, so you can see this angle is increasing. But what's the maximum possible angle that this can take? What's the maximum possible angle that this angle of diffraction can take? Definitely, it will be smaller than 90 degrees if the fringes are supposed to be formed and produced and projected on the screen. Okay, so we realize that this theta has to be like smaller or equals to 90 degrees. So the maximum possible diffraction angle that can be achieved on one side will be 90. So in order to find all the maximum on this side, we will take the maximum possible diffraction angle to be theta, to be 90. Okay. Now the relevant equation that we will be using is going to be this one. So n lambda equals to d sine theta. Alright, let's use an equation here. We have n lambda equals to d sine theta. So n maximum lambda equals to d. D is a slit separation. In our case, it is 7 lambda. Oh, sorry. 7 lambda over 2 when angle is 90 degrees. Okay, so we will achieve maximum number of slits, maximum number of constructive interference when the angle is 90 degrees. So sine 90 is 190. Why 90? Because that is a maximum possible diffraction angle that will allow us maximum possible projection of fringes on one side of the plane. So just make a lambda cancels out, so n maximum will be 7 over 2. So, but realize this 7 over 2 is only on the top side of the projection screen. There is also bottom side of the projection screen where you have these maxima. So the angle can also go in the downward direction, again 90 degrees. So we have to consider both sides. So they will be like 7 over 2 maximum possible fringes there, and there will be also 7 over 2 equal number of maximum possible fringes there. Just multiply this thing by 2 to consider both sides of the plane. So this will give us 7. So 7 is the answer. Okay. Diffraction grating is used to observe light of wavelength 400 nanometers. So we have a light of wavelength 400 nanometers. So wavelength is 400 nanometer. The light illuminates 100 slits. So the number of illuminating slits is 100 slits of the grating. What is the minimum wavelength difference? So minimum wavelength difference. So we need to find this delta lambda. That can be observed when the second order of diffraction is second order. So m is actually the order, which is 2. Let me show you which equation we are going to use here. So we are going to use this equation. This one. So r equals to lambda over delta lambda equals to mn. So let me give you a brief lesson on what this equation is about. Okay, so it's a resolvence of grating. Okay, so you see, resolvence or chromatic resolvence power for a device is used to separate the wavelength of a light is defined as resolvence. So resolving power, resolvence is lambda over changing wavelength, where changing wavelength is the smallest resolvable wavelength difference. The limit of resolution is determined by the Rayleigh criterion as applied to the diffraction maxima. Okay, example, two wavelengths are just results when the maxima of one lies at the first minima of the other. So when the maxima and minima they coincide with each other. Since the space between the maxima for n slit is broken up into n minus 2 subsidiary maxima, the distance to the first maxima is essentially 1 over n times the separation of the main maxima. This leads to a resolvence of a grating of resolvence equals to wavelength divided by change in wavelength equals to m times n. M is the order of the diffraction. In our case it is 2, and n is the total number of slits illuminated. In our case it is 100. So I do encourage you to check out this website, it's Hybrid Physics, and try to read this page and try to also see some examples on resolvence and how to actually do them. Practice some questions from here too. Alright, let's go back to our questions. So the equation that is also given in the data booklet on resolvence is R equals to lambda over change in wavelength equals to m times n. What we need to find is this change in wavelength, so make change in wavelength the subject. So that will be equals to lambda divided by m n. So let's sum in everything. So our wavelength is 400 nanometer. M is the order, which is 2, times N is the number of slips, which is 100. Alright, so you can see this cancels out. 4 divided by 2 is 2 nanometer is the answer. So that's why 29 is B. Okay. What is a unit for capital G epsilon naught? So G is the universal gravitation constant, and E naught is the permittivity of free space. So for the unit, for the purpose of units, so we start like this. So G epsilon naught. So let's write it in terms of units. So what is a unit for G? So let's go back to our data booklet. First page, G. The unit for G is Newton meter square kg to the power of negative. So it's a Newton meter square kg to the power of negative. Let's see what is a unit for epsilon naught. It is a Newton inverse meter negative 2. So it's Newton negative 1 meter negative 2. Let's try to simplify this thing. So you can see this Newton and this Newton, they actually just cancel out each other. Because if you use the indices, 1 minus 1 is a 0. And these two also cancel out each other. Yeah. So, alright, it looks like we forgot to add the fourth unit here. See, sorry, we forgot to put C to the power negative 2. So there's also a coulomb here. So we should write C to the power 2. Is it 2 negative 2? 2. Okay, so just make sure that I put this 2. So we're only left with these two terms. So we have C square kg negative 2. There we have it. So we have coulomb square kg negative 2 B. Okay? Yeah, simple unit conversion. 31. Two parallel metal plates are connected to a DC, so direct current power supply, and electric field formed in the space between the plates as shown. Okay. What is the shape of the equipotential surface that results from this arrangement? So equipotential lines are the lines that cuts any type of field lines perpendicularly. For example, if you have these field lines, it can be either gravitational field lines, magnetic field lines, or electric field lines. This will be the equipotential, such that they cut magnetic field line perpendicularly. So equipotential lines are the lines along which, if you move something, a mass, a charge, or a magnetic field, depending what type of field it is, there is no work done. So there is no work done as we move along the equipotential lines, because there is no force acting in the direction of the equipotential line. So the equipotential surface here will be like, for example, it will be something like this. So perpendicular, 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 something like this. As long as this is perpendicular, so equipotential line cuts field lines perpendicular. So like it's going to be B, 31. 32. A satellite of mass 1500 kg is in the Earth's gravitational field. Okay, so probably there's Earth here, and this Earth has some gravitational field here. So these are the equipotential lines that I'm drawing actually, because actually the gravitational field is radial, and it's radially inward. Okay. It moves from a point where the gravitational potential is negative this much to a point where the gravitational potential is this much. So gravitational potential has increased. You can see it has become more positive. So if you look at the data booklet, you can find out the equation for the gravitational potential, which is actually this one. So it's Vg, gravitational potential is negative Gm over R. So how does it look like actually? This is how it looks like. So if you have a graph of Vg, which is in joule per kg, because it's energy supplied per unit mass, versus distance, which is r in meters. And imagine there's an earth here, and this is the center of the earth. This thing is going to look something like this. Like this, exactly. It's going to look something like this because there's a negative inversely proportionality graph. So in our case, so it looks like we are going from negative 30 to negative 20. Okay? So it means we were here, now we are here. So we are moving away from the earth. You can see, if you follow this path, you are moving away from the earth. Right? So it has to be away. In order to increase the gravitational potential energy, no, not the gravitational. This is gravitational potential energy. This is just gravitational potential. So in order to increase the gravitational potential or gravitational potential energy, you actually have to move away from the earth. So it has to be away from the earth. So ignore these two. This is the unit for gravitational potential. What is the direction of the movement of the satellite? And the change is just the difference between the two. So what is the difference between negative 30 and negative 20 and changing? So you can see changing what? Changing gravitational potential energy. So it's a little bit different from gravitational potential. So if you look back at the data booklet, so gravitational potential is, this is the equation that we will be using. Okay, this is the equation that we will be using. Let me just erase. And it's a little bit messy. Alright, good. Okay, so let's use this equation here. So we have gravitational potential energy is equals to mass times gravitational potential. So any change in gravitational potential is equals to mass times any change in gravitational potential. Yeah, so change in gravitational potential energy equals to mass times change in gravitational potential. So our mass, I remember, is 1500, yeah? And our change in final minus initial. So remember, it was like we're going from negative 30 to negative 20. So this is going to be 1500, and this is this is 10. So it's going to be 15000 megajoule of energy, because the unit for gravitational potential was in megajoule. So if you multiply one more, so we will get giga. So it has to be 15,000 megajoule, gigajoule. 32.8. Yeah. 30. Which of the following reduces the energy losses in a transformer? Using thinner wire for the wiring? No way, because the resistance, as we remember, is equal to resistivity length over area. So if you decrease the cross-section area of a wire, if you make a wire more thinner, it will increase the resistance. So bigger the resistance means bigger the power loss. So don't do that. Using a solid core instead of a laminated core? No. So imagine if you have this as a solid core and this is a laminated core. So laminated core has a lot of these laminated sheets that are actually joined together. So this is solid and this one is laminated. So the main difference in these two is, so in the transformer, in transformer the core, the metal conductive core of the transformer itself undergoes electromagnetic induction. So there are some eddies current produced in a transformer. Yeah, there's some eddies current induced in a transformer. So if the transformer core is made up of a solid bulk, then the current will have a much bigger space to move around. So the more current moves around, the more heat is going to dissipate. But if it is laminated means you have this metal sheet that are actually joined together by means of some insulation. So there's insulation between these metal sheets. If you see from a side view, if these are the two metal sheets, this is insulation. And then you have insulation, and then you have metal sheet. But this is the case, the current is only confined to move in a confined region. So it can't move freely anywhere. So if you limit the region of space in which current moves, you can actually limit the amount of power dissipated. Right? So don't do that. So use laminated. using a core made up of steel instead of iron? No. Uh, iron has a much uh, iron becomes a much better temporary magnetized material, and iron is a much better conductor than a steel, because steel is an alloy. It's not pure, so it has like carbon impurities into it to make it more stronger and stiff and brittle. So steel, being impure and alloy, has a higher resistivity than iron. So iron has a lower resistivity, so it is a better conductor. So don't choose this one. Linking more flux, so magnetic flux from the primary to the secondary. Yes. So this will make sure that there are minimum flux losses to the air or to the surroundings. So most of the magnetic flux is actually confined inside the metal core, and it is transferred from primary to secondary. And in the secondary, the electromagnetic induction takes place and the AC current is induced. So yes, choose D. A secondary coil of an alternating current AC transformer is connected to two diodes. So diodes only allow unidirectional flow of current. It doesn't allow any backflow of current, as shown below. Okay, so which graph shows the variation with time of the potential difference V of x between x and y? Okay, so we have these graphs. Yeah, let's zoom in here a little bit to see what's happening here. So let's do one situation here. So imagine, because this is AC transformer, so in AC transformer the current changes its direction, it becomes positive to negative, negative to positive. So let's draw. So this will become positive. So imagine this one case. The secondary coil of an alternating AC transformer is connected to two diodes as shown below. So diode only allows unidirectional flow of current. Okay, so it doesn't allow any backflow of current. So if we have a diode here, so it only allows current to go in the forward direction. It doesn't allow any backward flow of current. No. Okay. So it's AC, so it's alternating source, so it's continuously changing its direction and magnitude. Which graph shows the variation with time t of the potential difference between x and y? So let's observe. So because we have an AC source, so the potential terminals are continuously changing along with the amplitude. So imagine first case, if this is positive and this side is negative. So imagine, so it doesn't matter what is maybe happening here. So we know that this is positive, this is negative, and then in other cases will be negative and this will be positive. And for example, first case is if this is positive, negative. So imagine you will. So this is a primary source. If the primary source is alternating, then the secondary source will also be alternating. So you will also receive an alternating source. So imagine this becomes positive, this becomes negative. So what is the voltage of this entire line? But this diode will allow the current to pass through. Positive, right? Right, so this is positive, so this is a higher potential, and this is low potential, so the voltage will actually go here. Right? So it's a positive voltage, right? It's positive. So V of x is positive. Now what if you reverse the direction of the current? What if it becomes negative and positive? So it becomes negative, it becomes positive. So what do you think is going to happen? So this time, this line, so the current will actually try to flow downward, and this line, so this diode will allow the voltage to flow here, the current will flow, it becomes positive again, and the current will actually be blocked here, but the line will still be positive, right? So no matter if this is positive or negative, so no matter what the terminal voltages are, voltage between x and y will always be positive, and there will be no gap between them, because the moment there is a change in the terminal voltage, because when the negative becomes positive, instantly the x terminal can feel the voltage, right? So for example, yeah, if this side is receiving plus, and then when this side is going away, we are actually this part. Immediately after this side, positive side starts to grow. And then when this positive side starts to die out, the other side starts to grow positive. So no matter what the terminal voltages are, the voltage between X and Y will always be positive. So it will be A part. Okay, so it will be A part, diode problem. It's kind of like a half-wave rectification. So the current is being rectified. Full wave and half-wave rectification. Yes. A parallel plate capacitor is connected to a battery. Okay, parallel plate capacitor. So if we have a battery here, and then we have a parallel plate capacitor. What happens when a sheet of dielectric material is inserted between the plates without disconnecting the battery? So the battery is still providing a voltage of V, so the voltage stays the same. So the capacitor is like fully charged at a voltage of V supplied by the battery, so you are like kind of stuffing in some dielectric. Dielectric is the insulating material that is stuffed in between the two parallel plates in order to increase the charges, the ability of charges or the energy that can be stored. Okay. So what's going to happen with the capacitor? So first of all, the capacitance is unchanged. Actually, if you look at the data booklet, you will see that the capacitance does depend on dielectric material. Even if you keep the cross-section area and the distance between the two plates the same, change the dielectric, the capacitance will be changed. So yes, the capacitance changes. How does the capacitance change? Well, we just saw that this is the formula. So if you stuff in more dielectric, you're actually increasing the permittivity, right? So if you increase this, you increase the capacitance. So capacitance will be increased. The charge stores decreases. No, the total number of charge that can be possibly stored on this capacitor will be the same, because the amount of charge stored is actually depends on this battery. How much charge or voltage can this battery possibly provide? The energy stored. Right, what is the formula for the energy? Energy is half CV squared. So the energy is half CV squared. We already discussed that this voltage stored on this capacitor will be the same because it depends on the battery. As the capacitor is fully charged, half is constant. So we know the capacitance has increased because of the presence of this dielectric. If you increase the capacitance, the amount of energy, electrical energy stored on the capacitor will also increase. That is why 35 is increased. Potential difference just stays the same. Okay. Right. Three capacitors are arranged as shown. So two of them are in parallel, one of them in series. What is the total capacitance of the arrangement? So these are the two formulas. So the arrangement of the capacitors, the overall capacitance follows exactly reverse order for the resistances. In resistances, in parallel we divide, and in series we add. So in capacitance, they happen in the opposite way around. So you see we have two parallel capacitance. Let's find what is the total capacitance for a parallel circuit. So in a parallel circuit, we add them together. Don't use the parallel circuit formula. That is for resistance. So in capacitance, it's the other way around. 1 plus 1 is 2.0 farad. And then this and these two are in series. So if they are in series, we apply the parallel formula. So what is like 1 over C total is to 1 over 2 plus 1 over 2. So this will just give us 1.0 farad. Okay? C total. Or you can just divide this thing by 2, because these are the two capacitors in series. Just divide it by 2. So it has to be a pi. So 1 plus 1 is 2, and then 2 and 2 are in series. In series, we divide them. So we use the parallel circuit formula. So we divide by 2, which is 1. 36 a pi. Yeah. Pair production by a photon occurs in the presence of a nucleus. For this process, which of momentum and energies are conserved? Well, everything is conserved actually. If you consider this equation, This one, energy, this and this, both momentum and energy, they have to be conserved. Yes, always remember that. Paired production is actually the particle physics topic. By a photon occurring in the presence of a nucleus, for this process, which of momentum and energies are conserved? Both of them must be conserved. Momentum and energies have to be conserved. Yes, 7 is. Okay, 30. An electron of mass m has an uncertainty in its position r. So uncertainty in position r means this is equivalent to delta x. What is the uncertainty in the speed of this electron? So uncertainty in the speed. So we need to find a kind of delta v. Alright, so here now we will use this equation. Delta x is the uncertainty in position. Delta v is the uncertainty in momentum, greater or equals to maximum constant over 4 pi. So delta x times delta p greater or equals to h over 4 pi. Okay. Now also know that momentum is mass times velocity, and uncertainty in momentum is equals to mass times uncertainty in velocity. Okay. So let's substitute that equation here. So instead of uncertainty in momentum, we will say it is going to be mass times uncertainty in velocity greater or equals to h over 4 pi. Just ignore this greater or equal to sign, just make it equals there. It's easy calculation. Okay, just make delta v the subject, so that is what we are looking for. H over 4 pi m delta x. Well, delta x is just this r. So just replace this delta x by r. So if you do that, you will have uncertainty in velocity is h over 4 pi m r. So h over 4 pi m r is d pi. Okay. Which of the following observed during a radioactive decay experiment provide evidence for the existence of nuclear energy levels? So they are discrete nuclear energy levels. The spectrum of alpha particle energies, yes. And remember, alpha particles have discrete energy. The spectrum of beta particle energies, no. Beta particles, they have continuous energy. The spectrum of gamma ray energy, yes. So gamma electromagnetic radiations also have discrete energy because they contain these electron energy levels, and these electron energy levels are they possess discrete energy. So only alpha and gamma have discrete energies that can provide evidence for nuclear energy levels, whereas beta have continuous energy, because when beta comes out of an atom, it behaves like a free electrons that can move around with any free continuous velocity, giving us continuous kinetic energy. So it's going to be 1 and 3. Okay? What is a charge of an electron antineutrino? Okay. And during what process is an electron antineutrino produced? Okay. So remember, antineutrino is produced during beta negative emission, and the charge on electron so the charge on neutrino or antineutrino is always 0. Okay. So let me teach you how beta negative particles are actually produced. So imagine if you have a neutron. So neutron is neutral. So a neutron has a charge of 0. It has a charge of 0 and a mass of 1, right? So when a neutron decays into a proton that has a charge of +1 and a mass of 1, plus, because you can see we have to conserve charges, so the total charge on the left hand side is 0, hence the total charge on the right hand side must also be 0. We already have a positive charge, which is a proton, so there must be some negative charge produced here, which is actually beta negative, beta with a negative charge and approximately 0 mass, because it has a mass equivalent to the mass of the electron. plus an antineutrino is also produced. This is the full nuclear equations that is involved. So charge of electron antineutrino is 0. It has to be 0 because the charges are already conserved. And production of electron antineutrino happens during the beta negative emission. Alright.